Hello, and welcome to Let's Talk Tech with DeepCore Data. I'm John Brewer, the owner and founder here at DeepCore, where we're using education to help companies make the right technical decisions. Today we're going to talk about, at a technical level, how the internet works.
Now that you've heard about the benefit of IPv6's vast goldmine of potential addresses, here's the problem: adoption. Most of today's web servers and application servers cannot use IPv6, so it's like buying an SUV and being told you can only use it on a racetrack. Will people and corporations be willing to upgrade for an invisible benefit? Time will tell. Okay, enough on addressing. Let's dive into the protocol itself. The IPv6 packet bears only a cursory resemblance to the IPv4 packet. The two packets work on very different principles. So here's the IPv6 packet, starting with the header. In IPv4, the address used to be 32-bit, which has now been pumped up to a deluxe size 128 bits in IPv6. The IP header contains information about how packets can be delivered from its source to its destination. The IPv4 header used 13 fields to identify various control settings. IPv4's header's total length comprised a minimum of 20 bytes, or 5 32-bit words. The IPv6 header has only 8 fields, with a fixed length of 40 bytes. Let's break it down some more. First up is the version field, which is the first 4 bits of the packet. This value indicates that this is an IPv6 packet. This number is always 6. Easy. Type of service field. The differentiated services code point is the next 6 bits, and the explicit congestion notification is the next 2 after that. The differentiated services code point uses exactly the same codes as IPv4 to classify different types of packets, and the ECN likewise works exactly the same way. Now we start to see some deviation. The next 20 bits are the flow label. The flow label is new, and it does something interesting. If all of those bits are 0, it has no effect. If there's a number there, though, it tells the routers and switches along the way that all packets with the same flow label and the same source and the same destination should all be routed along exactly the same path. The next 2 bytes of the header are the payload length, the number of bytes in the packet's payload, including any extension headers. After the payload length is a 1-byte next header field. We'll get back to this beast in a minute, which means we're skipping ahead onto the hop limit field. This works the same way as time to live does in modern IPv4. It is decremented each time the packet is routed, and when it hits 0, the packet is dropped. New name, slightly different method, same ticking bomb. Finally, there's the source and destination addresses. Each address is 16 bytes long, so these fields combined are 32 bytes. These fields represent the sender and the recipient. Pretty straightforward, huh? So let's get back to that new and mysterious next header field. What, you must be asking, is that? The next header field indicates what kind of payload this IPv6 packet is carrying. It's roughly equivalent, and indeed uses the same numbers, as the IPv4 protocol field. So why isn't it just called the protocol field as it was in IPv4? Because this functionality has been extended to allow IPv6 to optionally include a number of ancillary fields that may be useful or even necessary as a packet moves across the network. These additional fields are called extension headers, and they share a common form. They each start with the type of the header that follows them, again essentially the protocol number, and the length of the current header in 4-byte blocks. There are 8 of these extension headers. If the next header is not one of these 8, it is the protocol number of the payload. IPv6 also comes with its own host of supporting protocols, such as Neighbor Discovery Protocol (NDP) in the place of IPv4's ARP, and ICMP v6. We'll cover those later. So we'll wrap up our introduction for now and go into detail in a future episode. But even at this early stage, you may be seeing some of the implementation issues starting to arise here. Consider a fully electric car. Lots of benefits, but without the infrastructure to support it, it's a hard sell. IPv6 has a lot of benefits, but they require new infrastructure. Without support, the question is it really better?
I hope you enjoyed this episode of How the Internet Works. If you like what you saw, please subscribe to our channel. If you have questions or an idea for a future episode, leave a comment below. I'm John Brewer for DeepCore Data. Thanks for watching.